Okay, today, 8th graders, we're taking a look at lesson 12 in your book. It's Modeling Using Similarity. It's on page 137 in your textbook. So 137. And example 1, it says, not all flagpoles are perfectly upright, perpendicular to the ground. Remember, perpendicular is a 90 degrees. So even though we want many of them to be straight up, some of them are at an angle. So some are what's called oblique in the math world, neither parallel nor at a right angle. So it's slanted. Imagine an oblique flagpole in front of an abandoned building. The question is, can we use sunlight and shadows to determine the length of that flagpole? So far we have the ground, that's the plane, and we have that oblique line, which is our flagpole. Now it says, assume that we know the following info, that the length of the shadow of the flagpole is 15 feet. There is a mark on the flagpole 3 feet from the base, and the length of the shadow of that little 3-foot section is 1.7 feet. So we can go ahead and draw this out. And when you draw this, you're going to be drawing a 90-degree line. It's going to be parallel because it's on the ground. So let me go ahead and we're going to take a look at this. All right, so, oops. I need that in the front. All right, so when we take a look at it, we can see I drew, or it is drawn. Here's still our flagpole. This OC is that 3-foot section, and the shadow cast was 1.7 feet. The entire flagpole is what we're hunting for. And then we have our shadow. We know that that shadow on the ground is 15 feet, 15, and it's labeled right here. So if we would connect our 3-foot section to its shadow, and we would assume the top of the flagpole to the end of its shadow. If we would do that, we see that we have 2 triangles given. And the question that we want to do is to find out how tall this whole flagpole was. Well, let's go ahead and I'm going to draw 2 smaller triangles. Okay, and they're not going to be perfect, but they're going to be triangles. And the first one right here, we had a 3, and it was 1.7. And on this one, we don't know the length, but we know this one is a 15. But what else do we know? Yeah, as you're taking a look at this, you can see that this angle O is the same in both triangles. And because we see that that's a shared angle, we have side angle side, the ASA. And therefore, we can set up a ratio, a proportion of this. We know that we have the length of the flagpole compares to the smaller triangle, as the length of the shadow of the flagpole is to the short shadow, the partial. And at this point, we can do our regular old math. We can cross multiply. So we have 3 times 15, which is our 45, and 1.7 times x is 1.7x. And now we need to get our x by itself. So we're going to have to do what to get both sides? Yeah, we're going to have to divide by our 1.7 on both sides, which cancels on the left. And 45 divided by 1.7 is 26.47 feet. So that shows us the height of our flagpole. Isn't it great that we can use real world situations in math? I know, it's crazy, right? I bet Hudson is just like rolling his eyes at me about right now. All right, you want to determine, we are on, the top of page 136. 136. You want to determine the approximate height of one of the tallest buildings in the city. You are told that if you place a mirror some distance from yourself so that you can see the top of the building in the mirror, then you can indirectly measure the height of similar triangles. So let point O be the location of the mirror so that the person shown can see the top of the building. So as we take a look at this and we see that mirror laying there, okay, automatically, because that mirror is laying there, it creates the angle that it creates right here, AOB, is 36. Therefore, the reflection angle is also 36 degrees. Okay, so we first have one of our angles. And they want us to explain why ABO, this triangle, is similar to STO, the larger one. So I'm going to go ahead and I'm going to draw our two little shapes, our two triangles. And I am going to flip this triangle around so that I have them and I can align my sides. Okay, so I know that my point of my triangle in both of these is 36 degrees because they share, there it was the same. And I also know that distance that he was standing away from the mirror was 7.2 feet. So I can put a 7.2 here. And his eyes from his head down was 5.3 feet. So I can put that over here. And where am I getting these pieces of info from? Down below, sorry. Right here, I'm sorry, guys. 5.3, 7.2, okay? And then we also know that the distance from the person to the base of the building, so this whole distance was 1,750 feet. Okay, now the goal is to find this height right here, which is supposed to be the height up here of this building that should have been a 90-degree angle. So this technically, not drawn to scale, should have been a 90 degree. That's the height here. How can we find the length from the edge of the building to the mirror? Nope, it's not 1,750. That's the whole distance all the way to the person. So we can subtract 1,750, take away the 7.2 that was the distance from our person to the mirror, and we get 1,742.8. So that's this number. And now we can set up our proportion, our ratio. So we can go ahead and put X, our height of our building. Let me scooch this up a little bit for us. We can X, the height of the building, over the height of our small triangle equals the distance of the building to the distance of the small triangle. And now we can do our bow tie, cross multiply. 7.2x equals 9,236.84. And then how can we get our x by itself? What's happening between the 7.2 and the x? Good, we're going to divide. Divide by 7.2. Divide the opposite side by 7.2. And our final answer then would be x equals 1,282.9 feet. There we go. And we're good. Go ahead and head back to the classroom.